Think circular motion and energy questions are an easy 2 marks. Think again. On the 2017 VCE Physics Exam, a massive 31% of students scored 0 on a basic tracking angle calculation, and a staggering 60% walked away with absolutely nothing on the roller coaster energy question. In this video, we are going to expose exactly where they went wrong so you don't make the same mistakes on your SACs and final exam. Let's get straight into it. A bicycle and its rider have a total mass of 100 kilograms and travel around a circular bank track at a radius of 20 m and at a constant speed of 10 ms1, as shown in Figure 6. The track is banked so that there is no sideways friction force applied by the track on the wheels. Because there is no sideways friction acting on the wheels, only 2 physical forces act on the system, weight and the normal force. Weight acts straight down toward the center of the Earth, while the normal force acts perpendicular to the surface of the banked track. The vector sum of these 2 forces produces the net resultant force, which provides the necessary centripetal force. Since the bicycle is moving in a horizontal circle, this net force must point perfectly horizontally toward the center of the circular path. Deconstructing common student errors. To maximize marks on this question type, students must actively avoid 2 frequent pitfalls highlighted in examiner reports. Adding fictitious forces. Students frequently draw a centripetal force FC or centrifugal force as an extra physical arrow. Centripetal force is not a separate force. It is simply the label given to the horizontal net result of the existing forces, Fn plus Fg. Misdirecting the net force, Fnet. Many students incorrectly draw Fnet pointing diagonally down the incline. This stems from confusing a banked track with a block sliding down a ramp. On a banked track, the vehicle maintains a constant altitude while moving in a horizontal circle, meaning its acceleration, and therefore its net force, must be strictly horizontal. Because there is no sideways friction acting on the wheels, only 2 physical forces act on the system, weight, gravity, and the normal force. Weight acts straight down toward the center of the Earth, while the normal force acts perpendicular to the surface of the banked track. From a geometric perspective, the normal force, weight, and the net resultant force form a right-angled vector triangle. By geometric similarity, the interior angle at the base of this triangle is exactly equal to the banking angle of the track. In this geometry, the net force forms the opposite side of the angle, while the weight forms the adjacent side. Consequently, the tangent of this banking angle is equal to the ratio of the net force to the weight. Here, the net force acts as the centripetal force required to maintain circular motion. By combining the centripetal force formula with our trigonometric identity, the mass cancels out, yielding the standard formula for calculating the ideal banking angle independent of friction. Taking the inverse tangent of this final quotient provides the precise angle of the bank. Taking the inverse tangent of this final quotient provides the precise angle of the bank. You can write this banking angle formula on your A4 cheat sheet to bring into the exam room. When a roller coaster car passes over the top of a circular crest, the 2 forces acting vertically on the rider are gravity pulling downwards and the track's normal reaction force pushing upwards. Because the rider is moving in a circular arc, the net downward force must equal the required centripetal force. To make the normal reaction force briefly drop to 0, giving the rider a feeling of complete weightlessness, gravity alone must provide the entire centripetal force. When we set the rider's weight equal to the centripetal force equation, mass cancels out completely, showing that this special speed depends solely on gravity and the sharpness of the track's radius. When the roller coaster car moves from the top of the track at point P to the bottom, point Q, in the absence of friction or an external driving force, only two forces act on the system, the normal force and gravity. Throughout the descent, the normal force remains constantly perpendicular to the instantaneous displacement and velocity of the car. Because the angle between the normal force and the direction of motion is always 90 degrees, the normal force does zero work. Since gravity is a conservative force and is the only force performing work on the car, no mechanical energy is lost to the environment as heat or sound, meaning the total mechanical energy of the system is strictly conserved. Bank track forces, SAQ7 A only weight, and the normal force act on the rider. Their vector sum is the horizontal net force pointing toward the center. Never draw centripetal force as a separate arrow. Ideal banking angle, SAQ7B from the right-angled vector triangle, tan equals F per milligram equals V squared, Rg. Mass cancels, so the friction-free angle depends only on speed, radius, and g. Weightlessness at the crest, SAQ8A. When the normal force at point P is zero, gravity alone supplies the centripetal force, giving V equals square root Rg, independent of mass. Energy conservation PQ, SAQ8B. The normal force is always perpendicular to motion and does no work, so mechanical energy is conserved. Use 1/2 mv squared plus mgh equals 1/2 mv squared to solve for the speed at q. Common pitfalls to avoid: don't invent fictitious forces, don't tilt F down the incline, and remember that horizontal circular motion requires a strictly horizontal net force. If you need my help, you can add me on WeChat or WhatsApp, or send me an email. Thanks for your attention. Please note Dr. Liu's VCE Physics channel, Dr. Liu's VCE Chemistry channel, and Dr. Liu's VCE Biology channel.